In the first 4 lessons of Chapter 9, we worked with operations with rational expressions. Now what we're going to do is we're going to actually look at functions that have rational expressions in them. So notice the definition of a rational function. So a rational function, f of x, is p of x over q of x, where q of x does not equal 0, which means the quotient can't be 0, which we know that can't divide by 0. And p of x and q of x are both polynomial functions. To start, we're going to evaluate some numbers that we want to put in for x into the function. So here we have f of x equals negative 3x squared over x minus 2. And we want to find f of negative 3. Well, we know that f of negative 3 is just the value that we get when we plug in negative 3 in for x. So this is going to be negative 3, and we're going to put negative 3 in, so negative 3 squared over negative 3 minus 2. Simplifying this, negative 3 squared is 9, so we have negative 3 times 9, and then negative 3 minus 2 is negative 5. So we get negative 27 over negative 5, which that's a negative over a negative, so we just get 27/5. Next we want to find f of 0, so we're just going to be putting 0 in for x, so we get negative 3 times 0 squared over 0 minus 2. Well, the numerator is pretty easy because 0 squared is 0 times negative 3 is 0. And in the denominator we have negative 2. We get 0. Next we want to plug in negative 2 into our function. We have negative 3, 2 squared over 2 minus 2. Our numerator, 2 squared, is 4. 4 times negative 3 is negative 12. And we get negative 12 over 0. Well, we all know we can't divide by 0. This is undefined. And that fits the case up here at the top under our definition of rational function. Q of x can't be 0, or when we put a value in for x, it can't make the denominator 0. So down in our example for this one, the denominator did equal 0, and so it's undefined there. Now we can find this last one, f of 4. So we have negative 3 times 4 squared over 4 minus 2. So we have negative 3, 4 squared is 16. So negative 3 times 16. 4 minus 2 is 2. We can reduce here since it's multiplying. 2 goes into 16 8 times. 2 goes into 2 once. So we have negative 3 times 8 is negative 24. And so that's just evaluating a function at different values for x. What we're going to do now is we're going to graph a rational function. And this is the main rational function or the parent function. To graph, whenever we come up with a new function that we haven't graphed before and we don't know the different ins and outs of it, what we can do is we can plug in some values for x. So let's just start off simple. Let's go ahead and we'll plug in those and then we'll see if we need anything else. So when we plug in negative 3, we have negative 1/3. Remember, y is the same as f of x. So we're going to put in negative 2, we get negative 1/2. We put in negative 1, we get 1 over negative 1, which is just negative 1. We put in 0. Well, we have 1 divided by 0, so we saw before that's undefined. So 0 is not part of the domain there because we can't put 0 in. Putting in 1, we get 1 over 1, which is just 1. Putting in 2, we get 1 over 2, which is 1/2, and next we get 1 over 3. So we're going to graph these different points and see if we can see what's happening. If not, we can always pick a few more points to graph. So we have negative 3 gives us negative 1/3, which is about right here. Negative 2 is negative 1/2. Negative 1 gets us at negative 1. 0 is undefined, so we won't have anything here when x is 0. Now over to the positives, we have 1 gave us 1, 2 is a half, 3 is 1/3. If we think through this, if we put in a 4, we get 1/4. So this would keep getting smaller and smaller. Same thing would happen here. But what's happening over here, like between negative 1 and 0, and between 0 and 1? So let's go ahead and pick a couple other points to put in here. Let's pick some fractions. Let's try 1/2. If we put 1/2 in there, we would get 1 divided by 1/2. Well, 1 divided by a half, that gives us 2, which means if we put negative half in, it seems we'll get negative 2. 1/3 gives us 3, and we could keep going. 1/4 would give us 4, 1/5, 5, 1/100th would give us 100. So graphing a couple of these points, if we put 1/2, we would get 2. If we put in 1/3, which is a little smaller than 1/2, we would get 3. 1/4 would give us 4. And then the same thing would happen with the opposites. If we put negative 1/2, we would get 2. Putting in negative 1/3, we would get negative 3. And so now we can look at our function and see what it looks like. I'm going to try to go ahead and trace over this. Remember, our graph is never 0, so it doesn't hit this axis. So it's going to come down, hit our points here, and keep going. It never does hit 0, because if you think about our fraction, no matter what number we put in there, 1 over some number never gives us 0, so it keeps getting closer there. And then this one's going to look similar, and it's going to look like that. Looking over on the right side, our graph keeps getting closer to the x-axis but does not reach it. It also keeps getting closer to the y-axis here but doesn't reach it, because if you think about it, we put in 1/100th, we would be way up at 100. But no matter what number you put in, you won't hit the y-axis because we can't put in 0 because we can't divide by 0. So in this case, the x-axis and the y-axis are both called asymptotes. The x-axis is a horizontal asymptote and the y-axis is a vertical asymptote. Looking at your paper there, you see that an asymptote is a line that the graph approaches as a number increases, but it doesn't ever cross. You do need to note that horizontal asymptotes can be crossed by the graph, just not at the ends, or the tails we call them. But vertical asymptotes can never be crossed. So horizontal asymptotes can be crossed, vertical asymptotes cannot be crossed. The last one we did was our main rational function. We're going to look at other rational functions. We're going to use these strategies to help us graph them. So refer back to these while we're graphing each of the following functions. We're going to factor the numerator and denominator. And looking at steps 2 and 3, the reason we factor them is because they help us find vertical asymptotes. So looking at, you find those by the values of x that make the denominator 0. Remember, the denominator can't be 0, so any x value that makes the denominator equal 0 will give us a vertical asymptote. Then we look at what makes the numerator 0. If the numerator of a fraction is 0, if we have 0 over 7, well, that's just 0. So anything that makes the numerator 0 gives us what we call a 0 or an X-intercept. So that will help us find where our graph crosses the x-axis. We can find the y-intercepts next by plugging in 0 in for x and finding out what y is. The last thing we'll want to do is graph some other points. That will help us see what the graph looks like between the different asymptotes. So I will work through these steps as we graph these next few functions. This first one here, we're going to factor the numerator and denominator. We obviously see that the numerator can't be factored, that's just 1. The denominator we can factor out an x, and we're left with x minus 2. Now we're going to find our vertical asymptotes by seeing what makes the denominator 0. So what values of x make the denominator equal 0? Well, if x equals 0, the denominator equals 0, because if we put 0 in for x here, that would be 0 times negative 2 is 0. Also, 2 would make the denominator 0, because if we put 2 in for x, that would be 2 minus 2 is 0, and 0 times 2 is 0. So those are the values that make the denominators equal. That's vertical asymptotes. So what we do is we draw some dotted lines at those spots. So x equals 0 is a vertical line. It's actually the y-axis. And x equals 2 is a vertical line that goes through 2 on the x-axis. So those are vertical asymptotes. Our lines will not cross those. In order to find zeros, or x-intercepts, those are values that make the numerator equal 0. So we look at the numerator. What values of x make 1 equal 0? Well, it sounds like a dumb question. Nothing makes 1 equal 0. So there are no x-intercepts. We also wanted to find the y-intercept. We can find the y-intercept by plugging 0 in for x. So the y-intercept, we're going to find g of 0. Well, that's 1 over 0 minus 0. So thinking back, we realize that there's no y-intercepts because there's a vertical asymptote there. But in other cases, we find the y-intercept by plugging in 0. So there's none. And so we can plug in some points now to see what our graph is going to look like. I'm going to plug in some points, maybe 1 or 2 over on the left here to see what's going on here. Then I'll plug in a point in between here, these two asymptotes, and then plug in some points to the right. So let's plug in negative 2. Plugging in negative 2, that would give us 1 over negative 2 times negative 2 minus 2. I'm using the second form of our equation here. Simplifying that, that gives us 1 over 8. So 1 point, that is negative 2, 1/8. So negative 2, 1/8 is way down here. Let's plug in negative 1. That would be 1 over negative 1 times negative 1 minus 2. Well, that's 1 over negative 1 times negative 3, which is 3. So that gives us the point negative 1, 1/3. So that's about here. From our last graph, from the parent graph, we can remember, well, this is going to, our graph would then look like this, because it's not going to hit the x-axis coming this way, and we know there's a vertical asymptote on the y-axis. Now I'm going to choose a point between the two asymptotes, so I'm going to choose 1. When I put 1 in there, I get 1 over 1 times 1 minus 2, which gives me 1 over negative 1, which is negative 1. So I have the point 1, negative 1, which is down here. Now I know both of these asymptotes are vertical asymptotes, so my graph can't touch it. I also know that there's no x-intercepts. That means that my graph will not cross the x-axis. So this portion here is going to come up, it's going to hit this, and then it's going to go back down. I know that it doesn't keep going up because it does not cross the x-axis at all. So it has to look like that. Now let's pick one point to the right of this x equals 2, so let's choose 3. Choosing 3 gives us 1 over 3 times 3 minus 2, which is 1 over 3, which gives us the point 3, 1/3. We can graph that point. 3, 1/3 is here. If we remember, we had a negative 1, 1/3, so the similar thing is going to happen here. This is a vertical asymptote, so it can't hit there. It goes through this, and then we have a horizontal asymptote here. There are several types of rational functions. but the ones that we work on this course are proper rational functions. And with these types of functions, the x-axis will always be a horizontal asymptote, and so we can know that. Next we have y equals x squared. So earlier we had the main one, y equals x. Well, this is y equals x squared. There's nothing here to factor, so we don't have to factor the numerator and denominator. But the denominator, we still want to find our vertical asymptotes, and those are the values of x that make the denominator 0. Well, the only thing that would make the denominator 0 is when x equals 0. So that's a vertical asymptote. We will put a dotted line to show our vertical asymptote. Our x-intercepts are the values that make the numerator 0. This is like our last case. There are no values that make 1 equals 0, so there are none. We could try to find our y-intercept by plugging in 0 for x, and this happened before too. We put in 0 here. Well, that gives us a 1 over 0, which is undefined, which we would have known that from the fact that x equals 0 is a vertical asymptote. And then we want to graph a few points, or choose a few points to help us graph this. So here's our x, h of x. This one should be pretty easy. If we put in 1, we get 1 over 1 squared, which is just 1. If we put in 2, we get 1 over 2 squared, which is 1/4. Now we could see a pattern. 3 would give us 1/9. Let's try negatives. If we put in -1, that's 1 over -1 squared. Well, -1 squared is just 1, so this is just equal to 1. -2 is 1 over -2 squared. -2 squared is 4, so this is a positive 1/4. So notice here we'll never get any negative numbers. This is a proper rational function, and so we know the x-axis will be an asymptote. And so let's graph a few of these points. We have the point 1, 1. We have the point 2, 1/4. We have the point -1, 1, and -2, 1/4. And here, forgot 3 and 1/9. So let's graph these. Here's 1, 1. 2 is already down at 1/4. 3 is 1/9, even closer. And so we notice here we have our asymptote here coming down to a horizontal asymptote. We also had the point -1, 1 and -2, 1/4, and so that's going to look the same but on the other side. And that's our graph of h of x, which is 1 over x squared. Our last function to graph here is x minus 1 over x squared minus 2x minus 3. We would factor both the numerator and denominator. The numerator does not factor. The denominator can factor into x minus 3 times x plus 1. Vertical asymptotes are the values of x that make the denominator 0, because we can't divide by 0. So we see that x equals 3 would make the denominator 0 if you put 3 into this part, and -1. So let's graph those. X equals 3 is a vertical asymptote, and x equals -1. Since this is a proper rational function, we know the x-axis is a horizontal asymptote. We can find our x-intercepts, values that make the numerator 0. X equals 1 would make the numerator 0, so that's an x-intercept. So we can graph x equals 1. Here's a case where our graph will cross a horizontal asymptote. We can find our y-intercept by plugging 0 in for x. So y equals, we would have 0 minus 1 over 0 minus 3 times 0 plus 1. That gives us negative 1 over negative 3, which is just equal to 1/3. So we have a y-intercept of 1/3. So that's down here at 1/3. And again, we could choose a few more points to help us find what this graph will look like. We'll choose some points to the left of this asymptote, x equals negative 1. So let's choose negative 2. If we put negative 2 in there, we get negative 2 minus 1 over negative 2 minus 3 times negative 2 plus 1. That gives us a negative 3 in the numerator. This part would be negative 5 times negative 1 is 5. So we have the point negative 2, negative 3/5. So negative 2, negative 3/5. Which, judging from our asymptotes, this part or branch of the graph would look like this, because there's no x-intercepts there, so it doesn't cross the x-axis, and we have this vertical asymptote. We have a few points in this middle section already. I kind of have an idea of what it will look like, but let's go ahead and figure out what 2 would equal. So put 2 in for x. We have 2 minus 1 over 2 minus 3 times 2 plus 1. That gives us a 1 in the numerator. This is a negative 1 times 3, which is negative 3. So that would give us negative 1/3. And because of our vertical asymptotes here, we know that this graph will look like this. It does cross through the x-axis, because we had that x-intercept. So that's what the middle part looks like. And then we want to find what the graph looks like on this right section. So let's put in 4. That would be 4 minus 1 over 4 minus 3 times 4 plus 1. That gives us 3 in the numerator. This is 1 times 5 is 5, so 3/5. So we have 4 3/5. And because of our asymptotes again, we can tell that our graph would look like this. And that's graphing rational functions. So again, what we do is we factor both the numerator and denominator if possible. The values of x that make the denominator equal 0 gives us our vertical asymptotes. The values of x that make the numerator equal 0 give us the x-intercepts. We can find our y-intercept, and then just plugging in some points and using the asymptotes, we can find what each part or each branch of the graph will look like.